So far, we've been integrating functions which are continuous on some closed interval. The fundamental theorem of calculus tells us that the definite integral of that function on that interval is then found by first finding an antiderivative of the function, evaluating it at the endpoints of the interval, and then subtracting. Well, what if we want to find the integral of a discontinuous function, or integrate over an unbounded interval? Well, then we're going to use something called an improper integral. The first type of improper integral is the kind where we're integrating over an unbounded interval. Now, it is possible for an unbounded region to have a finite area, as in the following example. What is the area between the curve y equals 1 over x squared and the x-axis, to the right of x equals 1? Well, we can't really compute that, but we do know how to compute sort of a truncated version of it. We can integrate from 1 up to some point t, where t is some very large number, and we can compute that area as follows. This is just a normal definite integral, so first find an antiderivative, and then evaluate at the endpoints and subtract, and then simplify. But then what we can do is let this right endpoint, t, go to infinity. And so we can just say that the improper integral from 1 to infinity of this function is just the limit, as t goes to infinity, of this definite integral, which we've already computed. Then we see that this limit is equal to 1, and so that total area, not just the shaded part, but also to the right of t out to infinity, that whole area is equal to 1. This unbounded region has area equal to 1, and we've computed it using this improper integral. Okay, so now I should probably define my terms more clearly. If we have a function which can be integrated from some left endpoint a up to any right endpoint t, then the integral from a to infinity is just the limit of the normal definite integral from a to t, sending t to infinity. Similarly, if f of x is a function which can be integrated from t to b, where t is any number less than or equal to b, then we can define the integral from negative infinity up to b this way, just by integrating from t to b and then letting t go to negative infinity. The improper integrals of these types are called convergent if the corresponding limits on the right side exist. Remember, limits may or may not exist. If the limits do exist, then these integrals are called convergent, otherwise they're called divergent. Now, if both of these integrals, these improper integrals, are convergent, then we can add them together and we should get the integral of the function from negative infinity up to infinity. And so, reading that backward, if we want to integrate a function over the whole real numbers, then we can split it up into two improper integrals, which are improper just on one side rather than on both. Okay, an example of a divergent integral is this: 1 over x dx integrating from 1 to infinity. Well, we first rewrite it using a limit. We convert this to a normal, proper, definite integral from 1 up to some t, and then we let that t go to infinity. Okay, well now this definite integral from 1 to t is a perfectly sensible thing which we know how to compute. First find an antiderivative and evaluate using the fundamental theorem. Plug in that right endpoint, plug in the left endpoint. Okay, natural log of 1 is 0, so I'm going to omit that term, and now we're just going to compute this limit. Okay, but as t goes to infinity, natural log of t also goes to infinity, and therefore this integral is divergent. So compare the two integrals that we've computed. In the first example, we saw that this area was finite, where this is meant to extend off to infinity to the right, and we've just computed that this area is infinite. So both regions are unbounded, but you can probably tell that on the left the curve sort of approaches the x-axis more quickly than the curve on the right. So that makes all the difference. And this approaches the x-axis quickly enough so that the area is finite, whereas this approaches the x-axis a little bit too slowly for the total area to be finite. It's going to be an infinite area. Now let's compute the integral of the function 1 over 1 plus x squared, integrating over the whole real numbers. Well, I'm going to divide this up into two. I could have split this up anywhere I like, but I chose to split it up at 0 simply because that seems like a natural choice. And now I can treat both of these integrals separately. And I'm going to start by noting that the antiderivative of 1 over 1 plus x squared is arctangent. And so let's focus on this first improper integral first. We rewrite it using a limit. It's just the limit as t goes to negative infinity of the integral of this function from t to 0. Okay, well, the integral from t to 0 is given by the fundamental theorem of calculus this way. And I evaluate at the right endpoint arctan of 0 minus the left endpoint arctan of t. Arctangent of 0 is 0. And if I let t go to negative infinity, then arctangent of t will go to negative pi over 2. And so that negative will cancel with this negative, giving me pi over 2. Okay, next let's focus on this integral. Same method. First we rewrite it using a limit. This time t will be going to infinity, and we're integrating from 0 to t. Okay, well that is equal to this expression by the fundamental theorem. Let's now evaluate at the right endpoint and the left endpoint, and to subtract. Again, arctangent of 0 is 0. And then if I let t go to infinity, arctangent of t goes to pi over 2. And so I get pi over 2 for that integral as well. So the sum of those two is just pi, and therefore this integral is pi, which shows me that the total area under that curve, 1 over 1 plus x squared, is equal to pi. For which values of p is the integral from 1 to infinity of 1 over x to the p convergent? We already know that if p equals 2, then this integral converges. That was our first example. And if p equals 1, then this integral diverges. So it'd be nice to be able to tell, just by looking at the value of p, whether this integral converges or not. So let's leave p unknown for the moment and try to just compute this integral. Well, to do so, I would first compute the integral from 1 to t, because then I'm going to let t go to infinity afterward. So to do that, let's compute by the power rule, and this is a typo. That should be a 1, and that should be a t. And then by the fundamental theorem of calculus, we evaluate at the right endpoint minus evaluating at the left endpoint. So the improper integral from 1 to infinity is found by taking the limit of t going to infinity of that expression. So the question is, when does this limit exist? And the answer is, it exists precisely when this limit exists, t to the 1 minus p. And that exists if 1 minus p is less than 0. And that's the same as saying p is greater than 1. So this integral is convergent if and only if p is greater than 1. So let's see what that means. So here's the curve y equals 1 over x, and we know that the area to the right of 1 under this curve is infinite. But then once p is greater than 1, say p equals 2, then you can see this tail kind of gets decreased substantially enough that now the area is finite. And indeed, if we increase p further, then that curve, that tail becomes even smaller. And so this sort of makes sense that if p is greater than 1, then the total area under that curve to the right of 1 gets smaller and smaller. And so the cutoff point apparently is p equals 1. If p is 1.001, for example, then the total area to the right of 1 would be finite as opposed to infinite. Okay. The second type of improper integral is involving discontinuities. If we have a function which is not continuous on the full closed interval, and we're trying to integrate over that interval, then we have an improper integral. So here's a typical example. What if we have a function which has, say, a discontinuity at the left end point of the interval? Well, then we can still try to integrate this if we, instead of computing the integral from a to b, what if we compute it from t to b, where t is then going to approach a from the from the right in this case? Well, then that's what we can do. We can integrate the function from a to b by instead computing the integral from t to b and then letting t go to a from the right. Or if the function was discontinuous at the right end point of the interval, then again we compute the integral from a to some value t, and then let t approach b from the left. Let's see how this can be done. To evaluate the integral from 2 to 5 of 1 over square root of x minus 2, we should be cautious and note that this function is continuous not on the closed interval from 2 to 5, but on the half-open interval from 2, excluding 2, up to 5. And so what we should do is compute the integral from t to 5 and then let t go to 2 from the right. So to do that, I'm going to do substitution. Let u equal x minus 2, then du is dx, and I can rewrite the integral like this, changing the limits of integration as well, and then using the power rule. And then I plug in the right endpoint and the left endpoint and subtract. Okay, well then now I'm ready to let t go to 2 from the right. So for the first term there's nothing to do, and for the second term I just get 0, and so the answer is 2 times the square root of 3. Now you might have thought that you could just write this. If you weren't paying attention, you might not have recognized that this is an improper integral at all. And so you might have computed the antiderivative correctly and gone ahead and evaluated at the endpoints, and you would have gotten the right answer. However, this is wrong because the integral is improper, and so you have to treat it as such. Let me emphasize this point as follows. Suppose we tried to compute this integral. Well, it looks like a non-threatening integral, right? It's just 1 over x minus 1, whose antiderivative we can find, and it's integrating from 0 to 3, so it doesn't look that tricky. However, if we weren't paying attention, we would just find the antiderivative using a substitution, and we would get natural log x minus 1, and then we would evaluate at the endpoints and subtract. And we would get the answer natural log of 2. However, this is wrong because this is an improper integral, and we did not treat it as an improper integral, and so that is wrong. Let's now do it correctly. Well, the function is continuous everywhere except at x equals 1, and 1 does lie in the interval from 0 to 3, so this is improper. We have to rewrite the integral this way, from 0 up to the discontinuity at x equals 1, plus from 1 up to the right end point of the interval. And now we can treat these two improper integrals separately. Now, since we already know this antiderivative, we can take that first integral from 0 to 1 and compute that as the integral from 0 to t, and then letting t go to 1 from the left. And we can use this antiderivative and then plug in the right endpoint and the left endpoint. Okay, now to compute the limit as t goes to 1 from the left of natural log of absolute value of t minus 1, we just consider that if t goes to 1 from the left, then the absolute value of t minus 1 goes to 0 from the right. And therefore the natural log of absolute value t minus 1 goes to negative infinity from the right. So that should in fact say minus infinity, but that's okay because that still is good enough to tell me that this is a divergent integral. And so if this integral from 0 to 1 diverges, and hence so does the integral on the full interval that we were approaching. So from now on, the phrase evaluate the integral, some definite integral, means that we first need to check whether the integral is improper, and if it's not, then you can just evaluate it normally. Otherwise, you have to first rewrite it using this limit notation. Then, if it's improper, the answer may be a number, if that limit exists, or the word divergent. So, which of these are improper integrals? Let's take a look at the first one and see if it's improper. Let's see, no infinite limits of integration, so that's so it's not improper of type 1. Maybe it's improper of type 2. Is this function continuous on the interval from 0 to 1? The answer is no. It has a discontinuity at x equals 2/3, and that does lie in the interval from 0 to 1. So this is an improper integral. So the first step in evaluating this would be to break up the integral from 0 up to that discontinuity, 2/3, and then from that discontinuity, 2/3, up to 1. And now you can compute these two improper integrals separately, and if either of them is divergent, then the original integral is divergent. Or if these are both finite numbers, then this whole expression will be a finite number. In fact, this one turns out to be divergent, which you can check for yourself if you like. Okay, let's check if this one is improper. We're integrating over 0 to 1, so there aren't any infinite limits of integration, so it's not an improper integral of type 1, though it might still be improper of type 2. So let's find where this function is discontinuous. I find that it's continuous on its domain, and its domain excludes the numbers 2 and 3. Okay, but both of the numbers 2 and 3 lie outside of the interval from 0 to 1, and therefore this is not an improper integral. You can evaluate this one normally without any trouble. Okay, this integral is clearly improper of type 1 because it has an infinite limit of integration. However, it's also improper of type 2 because this function is not continuous at x equals 2. X equals 0 is not in the domain of this function, and so this is improper on 2 counts. The first step in evaluating it would be to break it up into 2 pieces. First from 0 to 1, and then from 1 to infinity. Or, I mean, it doesn't have to be 1, it could be any number in between 0 and infinity. The point is that we need 2 separate cases, where t is approaching 0 from the right, and where the upper limit is approaching infinity. So let's go ahead and finish computing this one. Let's first compute the antiderivative of 1 over square root of x times x plus 1. I'm going to do this by letting u equal square root of x, and then du is equal to 1 over 2u dx, and I can rewrite the integral this way. And here I'm also changing the limits of integration. Okay, well now the u's cancel here, and this simplifies to just 1 over u squared plus 1, and so that's arctangent. Okay, so then we can replace this first definite integral with 2 arctangent of 1 minus arctangent of square root t, and the second one we're replacing with 2 arctangent square root of s minus 2 arctangent 1. And now we just need to compute these 2 limits. Well, if t is going to 0 from the right, then arctangent of square root t is just approaching 0. We can just plug in 0 for t there, and that's 0. And then as s approaches infinity, square root of s also approaches infinity, and so arctangent will approach pi over 2. And so we get 2 times pi over 4, because arctangent of 1 is pi over 4. This one was 0. This one was pi over 2 here. And that one, again, arctangent of 1 is pi over 4. Okay, that term is 0. And then this, the first and the fourth terms will cancel with each other. And then this 2 cancels with this 2, leaving me with just pi. Okay, there is a comparison test, which helps us decide whether some integrals are convergent or divergent. And the way it works is this. If you have 2 continuous functions on some interval, and one of them is always bigger than the other. Let's suppose that f always lies above g, and both of these are lying above the x-axis. Then we can say that if the integral of the larger of the 2 functions is convergent, then the integral of the smaller of the 2 functions is convergent as well, which is equivalent to saying that if the integral of the smaller function is divergent, then the integral of the larger is divergent. This makes sense because if the total area under the larger function is finite, then clearly the total area under the smaller function is finite, and vice versa. If the area under the smaller function is infinite, then the area under the larger function is also infinite. Now, a similar theorem is true for any type of improper integral. For instance, it could be of type 2, or it could be going to negative infinity. The fact that I've written a to infinity here isn't really that important. Any interval at all, this comparison test will work. As an example of this, let's compute this integral here. So this is a function whose antiderivative I don't think I know how to compute, but that's okay. I'm going to use the comparison test to do this. Since the exponential function is always non-negative, we can see that this whole fraction here, if I split it into 2 fractions, this will be at least as big as 1 over x, whenever x is positive. But we already know that the integral from 1 to infinity of 1 over x is divergent. And so this is a smaller function, this is a larger function. The integral of the smaller function is infinite, so the integral of the larger function is also infinite. So that tells me that this integral diverges, because it is bigger than a function whose integral diverges. Now always check the function for discontinuities when you're computing definite integrals, because you might be dealing with an improper integral. Rewrite improper integrals using an appropriate limit, as we showed in this lecture, and then you can evaluate that definite integral normally and then evaluate a limit. The comparison test can be used to prove whether certain improper integrals are convergent or divergent. This does require some practice though. In the next video we're going to start chapter 6, which involves applications of integration. But before we do that, I'd like you to try to explore improper integrals a little further. First explain why this integral is improper, then rewrite it using a limit, and then go ahead and finish computing it. To do this you can use either integration by parts to find the antiderivative of natural log, or by tables. And when you get to the point where you need to compute a limit, you'll need to use L'Hopital's rule.